Non-linear programming problem. So till now we have studied what are the linear programming problems. So in the case of linear programming problem, there was an objective function, and there are some conditions. But this objective function is of kind linear function. Okay, fx is a linear kind function. So there was some restriction condition part, and based on this we solve the problem. So in the case of linear problem, this function is a form of linear, so it will be like this, it will be like this, and we find what was the optimum point on that function. But there can be so many cases where the problem is actually non-linear, that means not linear in nature. Okay, so we can say that if the constant and function to be minimized are linear, this is known as linear programming problem. Otherwise it will be said as a non-linear problem. So if this objective function is linear, it will be linear programming, and if this objective function is non-linear, then it will be non-linear problem. Okay, let us take an example. Suppose fx is like 5x plus 4y equal to 1. So this is a linear equation. But if I am writing the same equation as 5x square plus 4y square equal to 1, so this is a non-linear equation. So in this way we can decide whether the programming methodology is linear or non-linear problem. There are a large class of decision problem that can be non-linear problem. So it was recognized that many times the practical problem cannot be represented by linear programming model, and because the method is going to be very famous, that means linear programming model is going to be very famous. So we have also to consider the other aspect of this, that means non-linear portion of it. This was firstly defined by the two scientists, and their name was Kuhn and Tucker. Kuhn, Kuhn and Tucker. Okay, these two scientists in 1951 has given this kind of concept firstly. So based on their concept, there are some point, because in the case of non-linear program, the main problem is to how to find the optimal solution. Because in the case of linear, you know that this is a linear function, these are the linear function, and this point will be termed as the optimum function. But if the shape of this function is non-linear, in that case it will be very difficult that at what point its value will be optimum, because the optimum value may be at this point, or at this point too. So we have to take this thing into consideration. So local optimum may not be global in this case. Okay, this is a local optimum of the function in this part, this is the another local optimum of the function in this part, this is the another local optimum in this part. So a local optimum may not be the global optimum in this case. This is the first concept. So in this case our aim is to find the local solution of the problem in place of global solution. Okay, so the Tucker concept was that in the case of nonlinear programming problem, we are going to find the local solution despite the global solution. So if suppose f and g are a convex function, suppose fx and gx are the convex function, then any local solution will be global. And this special class is termed as the nonlinear convex programming model. Okay, so this was the definition of what the nonlinear programming is. This kind of problem can be divided into two parts. One is unconstrained optimization, and the second one is the constraint optimization. Constraint optimization. What is the basic difference between these two terms? In the case of unconstrained optimization, the optimum value will be at a particular place. The optimum will be taken at a particular place. That means if there is a function like this, then we will consider only a particular region of the function and will try to find the optimum value at this function. So as you already know, there will be two things. One thing is that the derivative at this point must be 0, because if this is an optimum point, that means the derivative at this point will be 0. Okay, the derivative of function at this point must be 0. This is the first condition. And the second condition, that if it is maxima, optimum can be divided into two parts. One is maxima and one is minima. So if the double derivative is termed as Hessian also. Okay, so if double derivative of the same function is negative, it will be maxima, and if it will be positive, it will be minima when it is positive, and if it is negative, then it will be maxima. So in the case of unconstrained optimization, these are the two main conditions, and I am going to discuss these two things. So first one is unconstrained optimization. Unconstrained optimization. So unconstrained problem do not arise frequently in practice. However, the optimality condition for unconstrained problem are important not only for themselves but also for the fundamental role they play in development of many techniques for solving constraint optimization problem. Okay, this is written in the book. It is saying that the problem of our concern here is to determine whether a point x0 is a local or global minimum point of fx, or x belongs to Rn. So we have to find whether the point x0 is a local or global minima of the function fx. We have to find this one over the function Rn. Okay, what is Rn? Rn is the n-dimensional space. Okay, when it will be written as R2, that means 2-dimensional space. When it is R3, it is 3-dimensional space. So if it is written as Rn, then that means it is denoting n-dimensional space. So suppose this x belongs to the n-dimensional space. This point is a local minima. So if this point is a local minima, that means function of x0 must be less than or equal to function of x. Okay, every point of the space, okay, every point of the space must be greater than that minima point, because its value should be minimum at that point. So this should be the first condition. Now based on this, there is a theorem. The theorem is saying that let f be a real valued function. Let f be a real valued function. That means it has some real value on n-dimensional space and is differentiable at x0. Okay, x0 was the minima, as I already have said. Again, it is saying that if there is a vector d such that gradient of fx0 transpose multiplied by that vector should be less than 0, that means it is negative, should be less than 0, then there exists a delta greater than 0 such that f of x0 plus lambda multiplied by d should be less than f of x0 for all lambda belongs to 0 delta. It is saying that the theorem is saying that f is a real valued function and differentiable at x0. That means at x0 the function is a continuous function, because if the function is a continuous function, only then it will be differentiable at that particular point. If there okay, one thing is that this is the derivative of that particular function, because we have said that it is differentiable, that means the function is differentiable at that particular point. Because we are dealing with the matrix, therefore we have applied the transpose. Okay, d is a vector, so it is a row vector, and this is a row vector also, but I have applied a transpose, so it became a column vector, and therefore we can now multiply both of the things. So the derivative is saying that at what rate it is changing, at what rate the function is changing at a particular point x0. So if x0 is the point, okay, it is like a minima, so let us draw like this. Okay, so this is a point x0, so at this point its derivative must be 0. So we have find the derivative of the function like gradient of x0. What is the value of gradient? So if you apply the gradient, that means for any function, suppose the function is having so many variables like x1, x2, x3, okay, then you can write it as deba f upon deba x1, deba f upon deba x2, deba f upon deba x3, like this. Okay, so the gradient is to be written like this. So here so it has been written like this. Now I am going to prove it. Since f is differentiable at x0, we have f of lambda d, because it is differentiable. That means if we include some of the lambda here, then it will be like, by the definition of differentiation, it can be written as f of x0 plus lambda delta of f x0 t d plus lambda d alpha is a function and x0 and some function of d. Okay, you know that differentiation of these kind of function, that means the first function multiplied by differentiation of the second function multiplied by differentiation of the first function, and because this is the plus, therefore it has been written in isolated mode, and lambda multiplied by differentiation of the second function and second function, that means lambda d and differentiation of the first function, and it can be written like this. So this I am going to start from this point and will prove this one. So my objective will be like this. Again, now lambda is tending to 0, this factor is tending to 0, okay, where alpha of x0 lambda d is tending to 0, because lambda d is also tending to 0 as lambda is tending to 0. Okay, when lambda will be 0, then lambda d will be 0, and the function will depend on only x0 and it will be tending to 0 also. Hence we can write the above thing as, hence f of x0 plus lambda d minus f of x0 upon lambda, this will be equal to gradient of f of x0 transpose d by the definition of differentiable function. We can write this thing as gradient of f(x0) transpose d plus d alpha x0 lambda of t. This can be written like this, and again if lambda is tending to 0, in that case the above function will become f of x0 plus lambda d minus f of x0 upon lambda. This will be equal to, because this thing is going to be 0, therefore it will be gradient of f x0 transpose d, and it should be less than 0. It should be less than 0, because this thing is greater than 0. If one of the factor is deleted, that means this factor should be less than 0. So from the definition of limit, what can we say? From the definition of limit, so from the definition of limit, we can write it as f of x0 plus lambda d minus f of x0 upon lambda. It should be less than 0, okay, because there exists a delta greater than 0 such that for all lambda which are not equal to 0 and minus delta is less than lambda less than delta. Okay, so lambda is between minus delta to delta. So if lambda is greater than 0, we have from the above point we can write as if this is greater than 0, then this thing will be less than 0. So we can say that f of x0 plus lambda d should be less than f of x0, and it is what we were supposed to prove. So in this way the theorem get proved. So this was the first theorem which we have proved here. Likewise, there is one important theorem again, and we are going to prove that theorem also. So theorem number 2 is first order necessary condition. Its name is first order necessary condition. First order necessary condition. The theorem is saying that let the function f such that r to the power n is r1 be differentiable. Okay, this function is differentiable at x0 if x0 is a local minimum. If it is a local minimum, then we can say that gradient of f at that particular point is equal to 0. It is a simple differentiation equation, but we have to prove for the unconstant proof. Let the gradient of fx0 is not equal to 0. Okay, when we prove something, then we start from the contradiction. If this point hold good, what we do then for some j delta, if this is not equal to 0, then if we expand, because earlier we have said that what is the definition of delta? Deva of deva x, deva of deva y. That means all the variable on which x0 depends will be partially differentiated. So suppose there are some variable xj, so all the variable showing xj will be less than 0, because it is not 0. So either it will be less than 0 or it will be greater than 0. So delta of fx0 upon delta of xj is less than equal to 0, or delta of f of x0 upon delta of xj is greater than 0. There can be two cases in this case. So if we take the first case, then by multiplying a variable dj multiplied by delta f of x0 upon delta xj is less than equal to 0. Okay, thus if we select d equal to minus gradient of fx0, we have gradient of f x0 transpose and multiplied by this d. This will be, because the value of d is this one, therefore it will be multiplied by this one, and the gradient become the double differentiation, that means Hessian. It will become as Hessian. Double differentiation is called as Hessian, and because of this minus sign it will be written as f of x0 whole square. but by the above theorem, the theorem which we have proved above, but by the above theorem there exists a delta greater than 0 such that f of x0 plus lambda t is less than f x0, okay, for all lambda belongs to 0 and a minimum point delta. So this contradict the assumption that x0 is a local minimum, okay. तो अगर जो है गलत चीज़ लेके चले हैं तो यहाँ पर जो है कंट्राडिक्शन आ गया कि ये जो वैल्यू है वो आपकी मिनिमा नहीं है, देयरफॉर जो हमने माना था कि ग्रेडियंट ऑफ एफ x0 was not 0 was wrong, and therefore gradient of f of x0 will be equal to 0, hence proved, okay, hence proved. So these are the two important theorem for unconstant optimization, okay. Now we are coming towards what is the constant optimization. What is the constant optimization? So we take a problem nonlinear programming problem such that we want to minimize the function f(x) such that there is another function gix less than equal to 0 for all I from 1 to some point m. So where the function f and g are, where the functions f and gi are f such that r to the power n is tending to r1 and gi such that r1 is tending to r1, okay. So both are tending toward a single dimension, and we assume that both the function are differentiable, okay. Both the functions are differentiable. Both the functions are differentiable. So let the constant set be denoted by s, that is s equal to, this is s not delta, so s equal to x such that gi of x is less than equal to 0 for all I equal to 1 to m. So this is a constant, and if this constant satisfies, then we say that it is a constant optimization problem. So based on this particular constant set, we optimize the given problem, okay. So to develop the optimality condition for the given problem, we introduce some of the definitions. So one of the definition is feasible direction, okay, because there will be the set of feasible solution in this case. Therefore we are introducing a definition what is feasible direction. So the direction of D is said to be feasible direction because in the direction of D, D is a vector. I already have discussed D is a vector, and in the direction of that D, we get the feasible solution. Okay. Suppose this is a function like this. Okay. This is a non-linear function. Okay. So there will be a vector D. So in the direction of that vector D, we get the feasible solution, that at this point we get the optimum value. Okay. The direction of gradient is this one, and the direction of vector D is this one, and when the direction of the function multiplied by direction of D will be equal to 0, in that case D will be normal to that function. So direction of D will be reaching at a point where we can get the optimum value. Okay. Suppose we are at this point at this instant of time. Okay. So this will be a line. So when we move toward this direction, then this line will be coming toward this one. Feasible direction definition. So let S be a non-empty set in R. So a direction D is said to be a feasible solution. Is said to be in the feasible direction at X belongs to S if we do not leave the region S when making a sufficiently small move in the direction D. Okay. So I have discussed by figure, and I think you have understood this thing, what is the feasible direction. So there is another theorem that if x0 is a local optimal solution, the theorem is if x0 is a local optimal solution to the linear program, then the gradient of fx0 d should be greater than equal to 0 for all d belongs to d of x0. Okay. So I think I have already discussed this thing, that it will be equal to 0 because direction of the function and the direction of d. Okay. Direction of derivative of the function and direction of d should be greater than equal to 0, and at the minimum point it will become as 0. So this will be the theorem which we have discussed here. So in this way we can see how the feasible direction work. Okay. This way we can see how the direction work. Now tomorrow I will discuss the Kuhn-Tucker optimality condition. Okay. So today I am closing the session.